Okay, so I'm sorry I kind of lost track of time last lecture and went over time by a few minutes, so I'm sorry about that. But as a result, I'm going to pick up today where we left off last time, and I'm going to reintroduce principal components analysis. And then we're going to talk today about understanding the SVD and different perspectives on understanding the SVD and how this is actually related to principal components analysis. So the fundamental idea around PCA was one of dimensionality reduction, right? Is that I have some massive data set. Maybe I'm thinking about the multiple data sets about the human genome. I have entire sequences of DNA, and I want to try and understand how this might correlate to various disease outcomes. Or I'm doing kind of healthcare monitoring, and I have tons and tons of data about different kinds of patients. Or I'm trying to understand astronomical data. We have many, many, many measurements, and we're trying to make predictions based on this, right? There's lots of cases when your data volume is crazy, and you need to be able to understand this in some kind of reasonable way. And as humans, well, we can kind of draw things in 2D, maybe visualize things in 3D, and then kind of we end there, right? Can't really go beyond that. So these 1,000-dimensional data sets, while they're packed full of information, for us to be able to glean the important bits from that, we need to somehow be able to reduce the dimensionality of that big thing to something that is more manageable in some sense. And even if it's not just for a human to be able to understand it, but even if you wanted to use some kind of machine learning model to be able to process your data, putting in 10,000 dimensional vectors, 100,000 dimensional vectors is not necessarily the most efficient or even computationally feasible in many cases, right? You want to be able to do things with reduced compute. And if you can somehow capture the information that is in those 10,000 dimensions in 4 dimensions, 5 dimensions, 8 dimensions, wouldn't you want to do that, right? So that's the key idea that principal components analysis is trying to get you to. What are the principal components of the data that you're thinking about? Right, so we're thinking about something with a p-dimensional structure, or p-dimensional vectors. But maybe there is some underlying q-dimensional structure where q is less than p. And this q-dimensional structure might not be exact, but it might be good enough. It might be a good enough approximation to kind of get you to where you need, right? So that's really what we're trying to think about. So to set this up, last time we said, let's consider that we have a bunch of data vectors, x1, x2, xn. Let's say I have xn data vectors. Let's say they're all zero mean. Okay. And what do I want to do? Let's say I wanted to find the best one-dimensional projection vector. So in general, I want to think about this problem where I have p-dimensional data and q-dimensional structure. I want to find the underlying q-dimensional structure. But to start out with, I want to think about the setup where I have p-dimensional data. Okay? So each xi belongs to, let's say, Rp. But I'm going to set q to be 1. I want to find the best one dimension through which to look at my data, okay? And so, for example, if I had three-dimensional data, right? So that means I have vectors that are in R3. So let's say this corner here is my origin. I have x-axis, y-axis, z-axis. I have three-dimensional data here. When I want to find the best one dimension, that means I want to find that one-dimensional hyperplane. What is a one-dimensional hyperplane? A line, right? What kind of line? Is it any line? What has to be true for it to be a vector space? It'll be passing through the origin, right? So I want to choose that line passing through the origin such that if I take all of my vectors and I project them onto that one line, I will retain the most information underlying from the data, okay? So that's, for example, when P is 3 and Q is 1, okay? And why are we starting with Q as 1? Well, because 1 is easier than 2 is easier than 3, right? That's the general rule of mathematics, engineering, computer science, and also life. If you have a complicated problem, do the simple version first. It will help you think about the more complicated version, okay? Question?
Is it like a line of best fit?
We will define precisely what we mean in just a minute. The question was, is this a line of best fit thing? So it's not a line of best fit in the way that the least squares algorithm gives you a line of best fit. You're not thinking about data points as, so in least squares, when you think about data points, you're trying to find a line of best fit. You have these data points, something like this. A line of best fit is what is the kind of fit that allows me to predict y from x. That's not what we're going to try and do. We're going to try and capture the structure of the data itself. So there are variations, and we will talk about them next week, maybe. Definitely you will have some homework and discussion problems on how, what we're going to talk about from principal components analysis, and then we will use the SVD to talk about a notion of what is called total least squares, which connects what we're talking about in the principal component sense to the line of best fit that we will talk about in the least square sense, but we're not quite there yet. I need like 3 more lectures worth of material to get you there. But there will be a problem that will allow you to explore this. Yes?
What does that 0 mean, refer to?
What does that 0 mean? Oh, it means that the average of the xi's are 0. So basically, I don't have a bunch of data points. My data is not all around here, right? If my data was all here, the average of the data is something like this. It's saying that my data is all, if I take the average of my data points, that's 0. Okay, so basically it means that sigma xi, I going from 1 to n, 1 over n is equal to 0. Okay? Yes?
What is like the thing we're trying to optimize here? Is it like the variance?
I haven't told you yet. I mean, I told you last time, but you've probably forgotten, so I'll tell you again. Yes?
So just make sure all the 0 is here, so it's all 0 in every dimension?
No, it means exactly what I just wrote here, which is that the average of the data points is 0.
Just like say it's 2-dimensional, like it's RP, right?
Yes.
Every dimensional is always 0?
No, not in every dimension. It's just the average of the data points. Like, I'm not sure I...
No, I just kind of want to make sure, like, right over here, that the diagram that you draw, it's x, y, right? Is it like in x and in y, they are all average 0? Or like...
I mean, effectively, yes, if you look at it component-wise, because your like average is the 0 vector, then every component of that is also 0, yes. Okay, good. So what are we trying to do here? Well, we are trying to minimize, basically we're trying to find the best one-dimensional projection. So we've decided that this is now a direction, right? This is a line which basically it's a direction. And I'm going to choose my w such that my w is unit norm, right? I want to find that direction that I want to project into. And I want to minimize. What is the minimization that I'm going to do? Very important question, right? I want to find the one that has the minimum error. So if I define my error of vector I to be, let's say I take my xi, right? So xi is my original data point. And I want to look at the difference between my original xi and my projection onto my chosen direction. Okay? This difference, and I'm going to look at the 2 norm of this. That is the error. That's basically how much am I losing? That's one way. Is this the only way in which we can measure error? Of course not, right? One of the things about optimization is choosing your loss function, choosing what you're trying to minimize. Here, we're choosing this way of looking at the problem. We're choosing to minimize the squared error between your data, your actual data, and the projection of the data onto the dimension of choice. Okay? And now, do we care about only the ith data point? Clearly not. We care about all of the data. And so what we're going to minimize, this is our optimization problem, is going to find that w that minimizes the average of the EIs. This is not a vector, sorry, this should be a scalar. Yes?
In some ways of teaching PCA, they describe it as like maximizing the variance along the projection. Is this equivalent to that?
This is equivalent to that. If I have time, I'll show you why. The maximizing the variance perspective is a statistics way that they like to talk about it. And so just to clarify what this question was, so sometimes if you read a textbook or if you take another class, PCA is also defined as maximizing, finding that direction that maximizes the variance of the data. This particular interpretation also relies on using the zero mean assumption of the data. Depending on how you're planning to do principal components analysis, actually you may or may not actually need this zero mean assumption, but a lot of standard textbooks kind of expect you to have this zero mean assumption. So maximizing the variance is kind of this idea of, let's say I have my 3-dimensional data and I project it onto a line, right? So for example, let's say my data was all stacked up along the z-axis. Okay, so my data points were like all over here, okay? And there's no data anywhere else, okay? And then I choose to project along the x-axis. What is going to happen? I'm going to project all of these points down, and they're going to all cluster in this like little area here, right? And am I capturing the true, like what's happening in my data here in that sense? It feels like that's not the best direction, right? Instead, if I had my data spread kind of in this direction, what direction might you want to choose to predict it? The z-axis, right? If I just project it along the z-axis, then I might kind of get this maximum spread. And that is the notion of kind of maximizing the variance, because you're kind of getting this larger spread here in this kind of setup. And if you want to think about it intuitively, if you projected all of these down onto the x-axis, you're getting all these giant error vectors, right? Whereas if I had all my data spread here and I'm just projecting onto the z-axis, my error vectors are going to be tiny. And therefore, my average error is also going to be small. You can formally prove that these two are equivalent. If I have time in lecture today, I will do it, but I don't know that I'll have time. If not, you can look it up in textbooks, and kind of the heart of it is basically understanding how mean and variance are related. Yes?
So in that case, the length of the vector is like associated with the variance of the data points?
Length of which vector?
The one that you projected on.
The length, I'm always going to be projecting onto a unit vector. I'm never going to be projecting onto anything that's not a unit vector. Yes?
Is the zero mean assumption like a big assumption, or if we like standardize the data, is it pretty like standard to have?
The question is the zero mean assumption a big assumption? Well, big is relative. Yes and no. ask me this question again after we've talked about PCA, because I'll be able to answer it better again. But basically, intuitively, I can show you the picture here, which is that if I gave you a bunch of data points here, right? Let's say I have two-dimensional data, and I gave you a bunch of data points here, and I told you, give me one vector that kind of describes the direction of this data. You're going to pull out this vector. This mean vector is going to show up, right? Because, like, well, relative to the origin, where's your data? You know, it's kind of around here. Whereas if I demean the data, like I remove this mean and then I look at things over here, this vector isn't going to show up, right? And I'm going to get more the relative variance of the data points with respect to each other. So a little bit it depends on kind of what you're trying to get out of the data, which is why some textbooks will talk about it in the context of having zero mean. Other textbooks will talk about it necessarily. So you don't necessarily need to have either. But there's a lot of things I want to get through, and the zero mean assumption is like a small thing, so I don't want you all to get bogged down into this zero meanness. It just came up, but okay, last question.
So what's the difference between those two models? For least squares, aren't we also trying to minimize projections?
Onto what? Hold that question. It'll become clear in like 2 more lectures, or there'll be a specific discussion problem that talks about this. It'll become clear. If I go into that, I will never get through my lecture, so you're going to have to wait, unfortunately. Yeah, okay. So what I want to talk about is, like, we want to now minimize these things. Let me just show you this one thing. So what does this actually mean? So if I now take this xi minus right, this is the error term, and I want to analyze it. And we did this last time, and so I'm not going to do it particularly slowly today. But this is xi squared minus 2 inner product wxi plus and so that's just equal to norm xi squared minus w inner product xi squared. Squared. Okay. So this is our error term, and what we're trying to minimize is the average of the errors. I guess I could have a 1 over n here. Not that it really matters for the minimization, because my argument will be the same whether I divide by n or not. So I have this thing here, and now of this we observed last time, this term is just a property of my data, right? It is what it is what it is. I have no control over it. And so if I'm trying to choose what's the best w, if I'm trying to find my argument, this term doesn't matter at all, right? All that matters is this term. And so what I'm trying to do is I'm trying to minimize, so the argument, I guess, of w of this right is equal to the argument of w that minimizes the sum of my squares of errors. Right? These two problems are equivalent because this term does not matter. And now, the minimizer of this, I can also equivalently write as the maximizer of the same term without the negative sign. Okay? So here, I'm just saying that the first equivalence is I can drop these guys. The second equivalence is like I can minimize with a minus sign, or I can maximize without the minus sign, right? And you'll notice here that I'm now not writing min equal to max. I'm writing argmin equal to argmax, right? The w is the same. The values of these functions are obviously going to be different from each other. Is that point clear to everyone? Any questions about that? It's clear what I'm writing here? Yes?
Can you repeat it, please?
The argmin of this problem is the same as the argmin of the original problem that we're talking about, because these xi terms don't matter, because they're fixed. I have no choice over them. I have no control over them. And now, whether I'm minimizing this thing with a negative sign, I can alternatively choose to maximize the negative of it.
But do they have it's at the same position that this happens with argument and argmax?
So the minimizer of this will be the maximizer of this. Yes, that's what I'm saying, exactly. Okay, good. So we're going to now focus on this particular problem, which we think about as kind of the canonical least squares problem in some sense, okay? There's many different ways to write this. There'll be an entire homework problem on alternate ways to formulate this exact optimization problem. So you will understand this in a lot of detail. We're just doing one in class, okay? So what I'm going to do is I'm going to show you what this dimensionality reduction really means, okay? So here, let's say I have some, 500 data points, okay? And let's say I have 4 different clusters of them. So I'm going to make 4 different clusters centered at these 4 different means, okay? So I have data that I'm basically generating that looks like this. It's just 2-dimensional data, okay? I randomly draw these points, right? I'm really not doing anything interesting. I'm just generating random clusters of data points, okay? And I plot this, and well, I had chose 4 clusters at means 5, 5, minus 5, 5, minus 5, minus 5, and 5, minus 5. And so what I see is basically these exact 4 clusters here. Nothing particularly surprising. What is the dimensionality of this data? 2-dimensional, right? Okay, good. Now, what if I was to embed this data into a higher dimensional space, okay? In particular, what if I was to embed it into a 25-dimensional space? Well, visualizing 25 dimensions is hard. I do not know how to do it. If any of you do, tell me, and we will make $1 million together. But let's just think about how we could embed it into 3 dimensions, right? Which we can think about. So for example, I could take this picture that I've drawn like this and kind of just put it in the xy plane, right? And then I could embed this in 3 dimensions. Everyone see that? I could embed it from a slightly different point of view. I could embed it in kind of a plane that's diagonal to me, and if I do that, kind of, there's still 4 clusters here, but from the perspective that I'm looking, like 2 of the clusters have merged into each other, right? Do you see how if I rotate this plane, that would happen? Depending on what perspective you're looking at it from? Yes? So depending on how I look at this, I can do these embeddings in different ways. But basically, if I want to take a 2-dimensional data set and I want to embed it into, let's say, a 3-dimensional space or a 25-dimensional space, that means I'm multiplying it by a non-square matrix, right? I'm taking every 2 by 2 vector, and then I'm multiplying it by something that is now 25 by 2, right? If I want to embed it into a 25-dimensional vector space. If I take a 2 by 1 vector, multiply by a 25 by 2 matrix, I'll get a 25 length vector out, right? And that's one way to take my data and project it into this higher dimensional space, right? So that's exactly what we're going to do. Is now I'm going to make a random matrix of size 25 by 2, okay? It's a full rank matrix because it has 2 columns, so it has rank 2. And now let's just project this, right? So I do this, and I create this data set, right? So I have a d-dimensional data set, in which case my d here, my capital D is now 25. And now I've created this d-dimensional data set, okay? So what does this data look like in 25 dimensions? Well, I do not know how to visualize it in 25 dimensions. So let's pick 2 random dimensions and project our data back down into those 2 random dimensions, okay? So we're not picking the same coordinate axis that we started out with. We're picking 2 different random dimensions, okay? So if I do that, I just picked, literally you can see I'm picking the axis randomly. And I project down, and this is kind of what my data looks like. So, it's not the original perspective, right? This is how I generated my data. The original axis would look like this. It's clearly in a different basis, but I can still see my clusters, right? There's 4 clusters, and I can still recover this. Okay. So everyone kind of understand this idea that you can have a 25-dimensional thing with an underlying 2-dimensional structure? Does it kind of make this more concrete? Okay, good. But now, of course, in our real world, we're not going to have such nice, clean, clustered data points, right? There's going to be noise, and things aren't going to look as pretty as we want them to be. So now, let's say I add noise to every single one of my clusters. In fact, I add a lot of noise. I add noise with standard deviation 5. Okay, remember my means were 5, so this is like a lot of noise compared to that compared to those means. I do the same thing. I do the same projection into 25 dimensions, and then projection back down to 2 dimensions. And now look at what my data looks like. All these clusters are kind of merged and blurred into one another, right? I cannot see those underlying 4 clusters that I had. Okay, good. So the question is now, can we use principal components analysis to recover the structure from the noise? And so what we're doing here is we have, I'm going to now take the singular value decomposition of this data set, and we will prove shortly why using the singular decomposition is the right way to do principal components analysis, or is a right way, not necessarily the only right way. And I do the SVD, and so I get out basically my V basis. I take the 2 columns of V, and I project back down along those axes. And you can see that I've recovered what was the original structure, right? Somehow, principal components figured out that there was a direction in which there is this structure that does maximize this variance, or that does minimize this error, and that particular direction preserves the underlying structure. Yes?
So is this exactly the same as what it looked like right after you applied the noise?
This is not exactly the same. It will have slightly different randomness, but the underlying structures and means are, you can see, are quite similar. It would still work. The question was, if I chose a different 25-dimensional matrix, would this still work? It would.
But just that when you project down to 2-dimensional, again, it would be different. Kind of different, maybe.
Yes, it would. So every time I do a random projection, I'm going to get a different random data set, right? However, because my original data had this structure, and my projection basically is a linear operator, and then in a sense preserved that structure, SVD is still able to recover that structure. Okay, so it's able to recover that there were 4 clusters of these data. And so if you're doing some kind of classification problem, for example, if your vector is representing medical data, and you will have you're trying to classify patients into patients who are high risk and patients who are low risk, and there was an underlying structure and dimensionality to it, PCA has a good chance of recovering that kind of structure.
But do we have access to the code?
What?
Do we have the access to
Do you have access to this code? I can see if I can make this code available. It's more like just something I wrote up, so it's not necessarily the nicest code, but yeah.
But when we add noise, like in which dimension to add those noise? In two-dimensional?
We added noise in all dimensions. So I added noise everywhere. Yeah. Yes?
So we know in this example we started out with a 2D data, then but in our case, if we just start with a high-dimensional data, how do we know which dimension we want?
Great question. So the question is well, you're you rigged the deck here, right? You said you knew you started out with a 2-dimensional data set. How would I know in general how to do this? So this example was designed as a pedagogical example. This is not how your data in real life is not going to look this nice. This was just me trying to teach you something. In general, one can do things like you compute many principal components, and you can say that, well, I will stop after my error goes below a certain threshold. So you can see you can also see the strengths of the singular values, which we'll come to, and you usually can pick how much of the singular values you want to capture, which also captures how much of the variance you're going to maintain. And all of this will become clear after we go through the math on this. Yes?
So for this question, we're projecting onto a two-dimensional plane in R3?
No, we're just projecting onto a 2-dimensional plane. So we're projecting 25-dimensional vectors into a 2-dimensional plane embedded in R25. Right? The R3 was just to show you what it means to go from a 2-dimensional space to a higher dimensional space, because I cannot plot a 25-dimensional space. Yes?
I feel like I see the benefits of projecting the lower dimensional space, but is there any benefits to projecting to a higher dimensional space?
Is there any benefit to projecting to a higher dimensional space? There are sometimes. You would almost never do that with data, but you do sometimes things called lifting of features, where you have a certain vector and you change it to become a longer vector because there's value to that. And we will come to that later, but you would not do that with data. Here, the only reason that I'm going from 2-dimensional to 25-dimensional is to show you what it means to have a 25-dimensional data set with an underlying 2-dimensional structure. This way you're convinced that there was actually true structure to begin with. If I didn't show you this and I just showed you a 25-dimensional thing and projected it into the 2-dimensional, you'll say, well, so what? So that was the reason that this was constructed this way. Yes?
Was the noise added in 25 dimensions or 2 dimensions?
25 dimensions, I'm pretty sure, but I could be wrong. 25 dimensions. But it would work, the same thing would work even if you added noise in the 2 dimensions. It wouldn't make a difference. Okay, good. So this is the key thing. Let me show you one more example. So again, can you read? Again, I don't expect you to read this in too much detail. But let's say, for example, you have some cloud of data that looks like this, right? And you want to identify the principal components. What are the directions of the data? Well, if you look at this, if you just had to tell me, what's the most important direction for this data? Could you do some hand motions to tell me what direction you would use? Yeah, right? And what's the second most important direction? Orthogonal to that, right? You go this way, and then around this way, there's a little bit of jigger up and down this way. Right? That's what it looks like. So, okay, good. So if I was to pull out PCA on this, I would get essentially these two vectors, this white. Can you see this? This white vector is light to see, but this would be the first principal component it would pull out. This would be the second principal component that it would pull out. Whoops. Okay. And now, if I was to project this, again, along my principal components, I could get data that looks, in a sense, much more evenly spread out, right? Because I'm choosing to look at it through the dimension of the principal component. So here, instead of having this in the standard basis, I'm projecting it, I'm doing a change of basis to project it along the basis of the principal component. So that's what kind of this projection looks like. Okay? But in general, like, there are more complex types of data that you might want to think about. And so, for example, one data set that is commonly used in machine learning models is this data set, which some of you might have heard of, which is called the MNIST data set. Okay? And there seems to be some inside joke that I don't know about, but I'm glad you're all excited about MNIST. Oh, you just did this in 189?
Yeah,
okay.
189.
Okay. So what is this? What is MNIST? Well, it's a set of digits that are written by hand. It's like images of, so it's images of these handwritten digits, right? And it's kind of one of the standard data sets that you start out off with when you're learning about machine learning. It's like an easier data set to work with. And so a thing that you might naturally want to do is you might want to look at an image. You might want to do OCR of some sort. Look at a digit and say, is this a 0 or a 1 or a 3 or an 8, right? Seems like a natural problem that you'd want machine learning to solve. So let's say you have this. And so now your data, it's a downsampled version of MNIST that I'm using for this demo. You have just 8 by 8 pixel images. So they have basically, you could represent them as a 64-dimensional vector, right? So 64 is already kind of a large size for a vector, right? We're already out of our league in terms of being able to visualize this in any effective way. So what if I did find the principal components of this data, right? So I have these 64 length vectors. I do principal components analysis, and I find the top 2 vectors, okay? And I say, give me the first 2, and I project along those. And now I project all of my 64, instead of plotting my 64-dimensional data, I plot them along principal component 1 and principal component 2. This is what my data now looks like. So the black dots all correspond to zeros. The dark blues are all 1s. The 2s are kind of a little bit mixed. The purples are 3s. The 5s are all oranges. So you can see that the colors are basically, like, the different digits have some kind of signature that is allowing them to cluster together, even in this noisy 2-dimensional perspective, right? Of course, if I was to choose 3 principal components or 4 principal components, maybe I could even refine this and pull this out even more in a better way, right? But it's just not that easy to visualize. It's just a quick 2-dimensional visualization to show that some structure is retained even when you maintain only the top 2 principal components. Okay? And so what do these components really mean, right? So for example, if I have, like, let's say this is my, this is a 0. So this is an 8 by 8 image of a 0. And so what I'm doing is, if I was to break this up into its component vectors, so for example, I could say, let me project this 0 onto the vector that is represented by this box, where there's a 1 in the first position and then zeros everywhere else, right? So what happens when I project this 0 onto this particular direction, right? I'm trying to find the best direction. What does PCA try to do? It tries to find the best direction. But let me just choose one direction. And if I was to project here, what would I get? Well, there's a white pixel here. There's a black pixel here. If I take the dot product of these, I get all these zeros, basically eliminating all of the information here. And the only pixel that gets preserved is this top left corner pixel, right? And so that's a 0, and so I get basically this blank square here. Then if I choose, let's say, something else, let's say I choose this particular vector. Is it clear to everyone how each of these boxes here is a 64 length vector? It's just represented like the 8, 8, 8, 8, 8. It's broken up into 8 times 8. Yeah? Okay, good. So I can project along each of these vectors, and let's say I add them up. So I take the projection along the first vector, second vector, third vector. And here I'm just choosing this one set of 8 vectors where I have a 1 and then zeros everywhere else, and then a 0 and then 1 in the second position and zeros everywhere else, and then a 1 in the third position and zeros everywhere else, and so on and so forth. And I'm choosing 8 such vectors. I project onto each of these 8 vectors, and I add them up. And what do I get? I get this, like, these little 4 pixels here are representing my 0, right? But none of this underlying structure of the 0 kind of has been maintained. It's very hard to tell from the 4 pixels that you're seeing here, or this image on the right-hand side, that the original thing that you did project was a 0. Does everyone see that? Right? Like, or does everyone not see the 0? Right? Okay. But now, instead, what if I chose the first 8 principal components? Okay? So if I do the principal components analysis, I get the first 8 principal components. And so I choose to project along this first dimension plus the second dimension, third dimension, and I take all of these dot products. So what is here is this dot product with this is this image. Then this 0 dot product with this is this image. And then I add all of them up, and I get out this final image, right? So does everyone see this as like how now, even though I've only projected along 8 vectors, right? So now if I wanted to store this, right, this is also a compression technique. If I chose my 8 principal vectors and I wanted to now store my data, once I've picked my 8 vectors, I just need to store the coefficients for each of those 8 vectors. If I wanted to represent my 64-dimensional vector, how many numbers do I have to store? 64. But to store the projections along 8 vectors, I only have to store 8 numbers. So I've suddenly reduced my storage quite a bit, and visually I can still maintain the structure. And so depending on what kind of application you have, like if you're going to be showing things only on tiny smartphones, maybe you can do with lower resolution images, right? And so we're going to talk about the Eckert-Young theorem and applications of SVD in this context as well in tomorrow's lecture, or Thursday's lecture. So keep that in mind. Yes?
So is that image on the right-hand side, is that the projection of the 8 vector factors in the four-dimensional space?
No, it is. So the right hand is the projection of?
These 8 principal components back into 64 dimensions.
No, it is a projection of the original image onto the 8-dimensional vector space represented by the principal components.
But that's 64 dimensions, right? Because it has the 64.
It's a 64 length vector, but that doesn't mean it's an underlying. So the like when I do a projection, right? Any projection, if I'm projecting a vector onto a vector, the 2 vectors have to be of the same length. This is an important question. Pay attention. If I have, like when I'm choosing this W, what is the dimension of this W? This is a p-dimensional vector. Okay? So I'm choosing 8 64-dimensional vectors. And I'm projecting onto those 8 64-dimensional vectors. Okay? So I can have, like for example, this plane is a 2-dimensional subspace that is embedded in a 3-dimensional subspace. Similarly, I can have an 8-dimensional subspace that is embedded in a 64-dimensional subspace. Right? Everyone with me there? So you can have vectors that are of some length, but the underlying vector space that is represented by those vectors, or that is spanned by those vectors, can be lower than that. Like just because I have a 64-dimensional vector doesn't mean that it spans a 64-dimensional vector space, right? So, yes, okay. So, this is kind of clear? Yes, question? How are these images vectors? So if I take any image, I'm basically rasterizing it. So if let's say I have a 4-pixel image, 1, 2, 3, 4. This is converted into a vector, 1, 2, 3, 4. For those of you in 16A, you did this in Lab 1, Week 1 for 16A. Yeah. Right? Take a 2x2 thing and represent it into just unroll it. So it doesn't matter how I draw it, right? This is just a way of drawing it. Does that make sense? Yes? Are the principal component vectors on the top still of norm 1? Yes, they are. In this case, basically, it's just a way of visualizing it, right? Yes?
Those coefficients on the second row represent the scalar of the dot product with the true.
It represents, yes. We're going to do all of this. Like, trust me, there is no shortage of math in this class. We will get to it, yes.
How often are the principal component vectors actually interpreted?
Question is, can you always interpret the principal component vectors? Sometimes yes, sometimes no. In this case, for example, I don't really have a particular interpretation of what these are. I can't visually see, but it depends on your application. Sometimes yes, sometimes no. Yes, last question.
Is there a reason the first coefficient is 1?
Is there a reason the first coefficient is 1? I think we've pulled out the mean here, so that's why it's 1. So here, this is not a zero mean example, right? The first principal component they've pulled out is actually the mean. Yes. OK. So I'm going to now do some math, and hopefully that will clear up the rest of the questions, because I think a lot of these are coming from like really what's going on, and we're going to talk about what's going on. So now, our goal is to find the first principal component, right? We're not yet talking about how to find the top k principal components. We're just trying to find the first one. And for that, we're going to solve this maximization problem over all w's that are norm 1 OK? And so how are we going to try to solve this? Well, one thing I want to introduce now is, let's say I have x1, x2, all the way up to xn. Okay? Basically, one standard way of looking at all of these data sets is to put them into a matrix. And I'm going to call this matrix X, x1 transpose, x2 transpose, all the way up to xn transpose. Okay? And a very important matrix that is often associated with data is the matrix X transpose X, which is called the covariance matrix. Okay? And what's one thing that you might notice about this X transpose X matrix? Symmetric matrix, right? Transpose of X transpose X is X transpose X. So there might be a reason that we've been doing symmetric matrices for, right? So we need to now understand this. So now if I think about this particular setup, I can actually rewrite this in a particular way, right? If I think about what is this quantity. So I'm basically taking the dot product of W with every single vector here, right? So this is x1 transpose W, x2 transpose W, x3 transpose W, blah, 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 blah. I can just write this as this matrix X times W, right? And that gives me the exact same thing, just squared, right? So I'm just rewriting this in a particular way. I did not use my board well. Well, you'll forgive me, I hope. What I'll do is this. I'll just erase this max so I don't have to keep writing it over and over again. I can rewrite this now. This is just the norm of some vector, which I can again rewrite as xw transpose times xw, which is equal to w transpose x transpose x w. Okay. So now I'm looking at this, and remember I have a maximization out here. So I'm trying to now maximize this over all norm 1 W's. Right? So the optimization problem I now have is maximize let me write this in a particular way to help you see it. How many of you know how to solve this problem? How many of you were in lecture yesterday? Well, no one, but last week.
Using the relay.
So what did we do last week?
Max of
Did we solve an optimization problem?
yeah.
What was that optimization problem? What was it called? What was the name? Rayleigh coefficient. What's the Rayleigh coefficient of a symmetric matrix? These are these maxima, like, is this connected?
The max of the eigenvalue.
Right, so if I wanted to find the max of this, what did we just say x transpose x is? Symmetric matrix. Okay, everyone, I'm going to put 1 minute timer. Open your notes from last week. And remind yourself of what happened. Actually, a 30-second timer. Be fast. So what form is this? What kind of form is this? What form is this called? We gave it a name last time. The quadratic form, right? And what is the value of this?
Scalar.
It's a scalar, yes. But what is the exact value? It's the largest eigenvalue of x transpose x. What is the W that achieves this maximum value? It is the eigenvector corresponding to that eigenvalue, right? So if I wanted to find the first principal component of a data matrix given by x, what do?
Find the biggest
I find x transpose x. I compute the covariance matrix, and I find the first eigenvector. Right? The first eigenvector corresponds to the first principal component. First eigenvector of the covariance matrix corresponds to the first principal component. So whenever you use NumPy or SciPy or whatever, and you call it PCA, all it's doing is it's an eigenvalue decomposition. Okay? Yes?
Any difference between this and XX transpose?
Yes, XX transpose will not do it in this case. And you'll see why that's the case. Because of the way you want to project your data. Because here you're representing your data along your rows, and so you want to project it this way. If you were to do XX transpose, your projections wouldn't quite work out.
Does that affect the interpretation if it maybe it's easier to compute it the other way because the dimension's smaller?
So it'll be easier for me to talk about this once we talk about the SVD, so hold that thought.
Like, what is the covariance measure? How is it related to the covariance in statistics?
It is basically the same thing as the covariance in statistics. You can compute it out, and you'll see how it's parallels. Yeah.
Isn't maximizing the square root norm of xw the same as maximizing the variance?
Is maximizing the squared true norm of xw the same as maximizing the variance of?
Isn't this the same formulation he was asking about with maximizing the projected variance? Like once you get to that expression?
Not necessarily, because you can show it, yes, because if you use the zero mean assumption, you can show that that's the case. But if you don't have the zero mean assumption, that's not. It's a yeah. So in some sense, yes, but.
Is that the covariance like equivalent to something like multivariable Gaussian?
Hold that thought. I don't want to go there. Just you can compute it out. It's not complicated, but yes. Okay. So how much time do I have? Where am I? Okay, good. So now, this is the first principal component, but we typically want to find far more than the first principal component, right? We want to find multiple principal components. And finding the eigenvectors of the covariance matrix is equivalent, essentially, to finding what is called the singular value decomposition of the original data matrix itself. And that's the standard way in which principal components are usually found. And kind of the first singular vector corresponds to the first principal component. The second singular vector corresponds to the second singular vector. The second principal component, and so on. And so kind of that's the standard way in which we end up finding principal components. So let me introduce the SVD, which you've all seen before. This is just review. Singular value decomposition. Okay? So what the singular value decomposition is it's given any matrix A, I can always write A as three matrices, U, sigma, V transpose. A is m by n. U is always m by n. Sigma is the same dimension as A, so it's m by n. And V is n by n. Okay? And this decomposition has some special properties. In particular, U and V are orthonormal matrices. Okay? And sigma is kind of almost diagonal. This representation that I've written is what is called the full SVD. And you can also write another version of this, which is the compact SVD. Where I can write A equal to UR sigma R VR transpose, where this is now M by R, this is R by R, and this is R by N, where R is the rank of the matrix A. Okay? Different people have different preferences on which particular style of SVD they like to use. My preference is to use the full SVD because you get nice properties of U and V being orthonormal matrices. Those don't quite hold in the case of the compact SVD, and you can't use these as liberally as you might otherwise want to. My recommendation to you, especially if you're like starting out in linear algebra, is to use the full SVD. It's easier to keep track of. But I know a lot of people like using the compact SVD as well. So there's different ways to go about doing this. The question is, how does one find the singular value decomposition? And that's what I'm going to kind of talk about next. So the singular value decomposition of matrix A is very closely connected to the eigenvalues of the matrix A transpose A. Not surprisingly, what you've just seen says that there's hints at this very, very strong connection, right? So now, if I have A belonging to M by N, what are the dimensions of A transpose A? N by N, right? So I have this N by N matrix. Wonderfully, it is symmetric, which means that I know all of its eigenvalues are going to be real valued. and I know all of its eigenvectors are going to be orthogonal. And I want to find like orthonormal things here, right? So this is going to be helpful for me. So let's say that this A transpose A has eigenvalues lambda 1, lambda 2, lambda r are the non-zero eigenvalues of A transpose A. Okay? Let's further say that it has corresponding eigenvectors v1, v2, vr. Okay? And these are now orthogonal. Let's just say call them orthonormal. I'll normalize them. Now, what I want to be able to do is I want to be able to somehow use this setup to be able to compute u, sigma, and v, right? So I have some things that are orthonormal, right? I want to use these somehow to make some u or v matrix, right? Like if someone hands me a stack of orthonormal vectors, I'm going to try and use them somehow. And so what we want to try and do is use these, figure out how do these kind of fit into this setup. And so what I know here is that I have A transpose A times Vi is equal to lambda I Vi, right? So what I'm going to do is I want to be able to do the following. I want to be able to define sigma I to be square root of lambda I. And I want to call this thing a singular value of A. Okay? I want to find the eigenvalues of A transpose A. And now I want to define sigma I to be the square root of that. Can I do this?
Yes, because they're all not zero, or greater than or equal to 0.
Okay, so I'm getting an answer saying that yes, I can do this because lambda i's are greater than or equal to 0. Do we know that?
Yes.
Why? Okay, so A transpose A is symmetric, and we proved that all of its eigenvalues are real as part of the spectral theorem. The spectral theorem tells us all eigenvalues are real. Do we know that symmetric matrices can only have positive eigenvalues? If I give you a matrix Q equal to -3, 0, 0, -4, what are the eigenvalues of this? -3, -4, right? Is this symmetric? Yes. Right? So can you have symmetric matrices with negative eigenvalues? Yes. So do I know that the lambdas are non-negative? It's A transpose A. Okay. So what do we need to prove? Aside. I think this is on your homework. Or you did it somewhere. Okay, take a minute and do this. Okay, so how do we do this? How do we show that what is special about A transpose A? Let's say lambda comma V is an eigenpair, right? That means that I have A transpose A times V is equal to lambda V for some eigenvector, right? Yes? Okay. Now what if I consider V transpose AV? What is this equal to? This is equal to V transpose lambda V, right? And if V is unit length, what is this? Lambda. Okay, good. But what is this? What can I write this as? Therefore, what must be true about lambda? Greater than or equal to 0, right? Okay, so because of this, I can define this. This is valid. I'm not getting singular values that are complex valued, right? This is a valid thing to do. Okay? So I define these sigmas this way. And now what I'm going to do is I'm going to define ui vector to be equal to be such that A times vi is equal to sigma I times ui. Okay? So I'm trying to get something that looks like this, right? And if v is truly orthonormal, then basically I have A times v is equal to u times sigma. Right? So here, I'm kind of, saying like, okay, if I wanted to shoehorn the v's to be in my v matrix, how could I possibly compute u's that might match? Okay? So I'm doing a little bit of pattern matching and say, let's try to guess and have this be the case. So what do we need to, if we wanted these u's to now form the columns of the matrix U, what would we need to show about these u's? We'd need to show that they're orthonormal to each other, right? Okay? So claim ui are orthonormal. Okay? So how do I check to see that these u's are orthonormal? What do I need to check for? If I consider the inner product ui, uj, if all of the ui's and uj's are orthonormal, what do I need to have? I want to have their dot product to be equal to 0, except when I equals j, in which case I want the dot product to be equal to 1. Okay? So let's compute this dot product, right? What is this dot product? Well, if I've defined these ui's this way, I can write this as basically, let's call this ui transpose uj. Okay? So I can write this as A times vi divided by sigma I. Remember, I'm only doing this for all of the, I've only defined these for the non-zero eigenvalues, right? So my sigma is therefore not 0. Therefore, I can take these square roots. Right? The lambdas I've pulled out to be the non-zero eigenvalues. Transpose times AVI AVJ, divided by sigma j. Right? I'm just substituting the definition here. So pulling out the scalars, this is sigma I, sigma j. And what I have here is VI transpose, A transpose, A VJ. Right? What is A transpose A VJ? What is VJ in relation to A transpose A? It's an eigenvector, right? Everyone's with me, right? Have I lost the class? No. Okay. You're with me. Okay, good. So A transpose A times Vj is lambda j. So I have this 1 over sigma I sigma j Vi transpose lambda j Vj. But now this lambda j is a scalar. So what is lambda j in relation to sigma j? It's just sigma j squared, right? So this sigma j cancels, and I get a sigma j remaining here. Everyone with me? Give me some thumbs up, nods, yes? Okay, good. You're just writing it down. Excellent. Taking notes is very, very good for your health. Academic health, and mental health, and everything. Okay, so now I have this sigma j divided by sigma I vi transpose vj. Okay? And so now, when I is equal to j, what is this? Vi transpose vj is equal to 1. Sigma is equal to sigma j. So this is equal to 1 if I equal to j. And when I is not equal to j, what is the property of our symmetric matrix? These are orthonormal, right? So this is 0. So we have now deduced that our u's are therefore orthonormal. Yes?
Where did you get the lambda j from?
Lambda j is because vj is an eigenvector of A transpose A.
Right, but like how did it appear in the equation?
This thing is equal to lambda j, vj. Okay, so now we've kind of done a part of our job, right? So we've found how many columns of v and u have we found? We've found r columns, right? We haven't found all of them. So how do we find the rest? If I have some vectors that are orthonormal and I want to find more vectors that are orthonormal, what do? Gram-Schmidt, right? So I use Gram-Schmidt to basically complete out the basis. Okay? And that gets me basically the columns of u and the columns of v as my orthonormal matrix. And just to verify, you can check to see, for example, if I take A times V, where let's say I have A times, so my RV, like I take V1, V2, all the way up to VR. These are my first R columns. And then I just complete out the basis, and let me just call this V null, because that's going to represent the basis for the null space of A, right? What is this product going to give me? Well, this is going to basically give me a matrix that is sigma 1 u1, sigma 2 u2, sigma r ur, and then zeros. Does everyone see that? And now this I'm going to be able to pull out into be exactly a diagonal matrix with sigmas along the approximate diagonal and columns of u, right? I can rewrite that first part as this, okay, with extra zeros appended. So that basically gives me that this forms the SVD, right? I'm not doing out that last bit of calculation, but you can verify it on your own. I have 1 minute left. I'll take a question. Yes? Why is this 0 here? This is 0 here because I and j are orthonormal. Vi and vj are orthonormal. Okay? So go back and remember all your linear algebra again. Review these notes. Do the homework. Go to discussion. See you tomorrow.